GE Aerospace clears key milestone for XA102 next-gen fighter engine. GE Aerospace has completed the Assembly Readiness Review for its XA102 adaptive cycle engine, clearing a critical design and manufacturing milestone in the U.S. Air Force's next-generation adaptive propulsion program and positioning the company to compete for the next program phase later this year. The ARR validates that the XA102 engine design, manufacturing processes, and supply chain are progressing on schedule according to GE Aerospace's announcement on May 11, 2026. Central to the milestone is a comprehensive digital engine model built on a model-based definition approach that replaces traditional two-dimensional engineering drawings with an integrated digital framework spanning design, manufacturing, and inspection. GE Aerospace has completed all model-based engine demonstrations associated with the first program phase, the company stated, marking the full closure of its Phase 1 technical commitments before the anticipated next phase award decision later in 2026. Dr. Steve Doogie, Russell Vice President and General Manager of Edison Works at GE Aerospace, framed the milestone in terms of both technical maturity and competitive positioning. With the completion of the Assembly Readiness Review, we are demonstrating the maturity of our XA102 engine design and the strength of our digital-first approach to developing next-generation propulsion systems, Russell said in the company's announcement. Our use of a fully integrated digital engine model which spans design, manufacturing, and inspection positions us to deliver advanced capability faster and with greater precision for the warfighter. The XA102 is the latest evolution in GE Aerospace's adaptive cycle engine lineage, building directly on the XA100 program that preceded it under the now discontinued Adaptive Engine Transition Program. The XA100 completed multiple successful rounds of testing that matured adaptive engine technologies and validated the core operating principles that the XA102 now advances. Adaptive cycle engines differ from conventional turbofans by incorporating a variable third stream of airflow that the engine management system adjusts dynamically based on flight conditions, optimizing either for fuel efficiency during cruise or thrust during combat maneuvering within the same flight. Earlier estimates from the ATP program indicated that adaptive cycle engines could deliver approximately 25% better fuel efficiency than the F-135, currently powering all three F-35 variants, alongside significant thrust improvements and substantially greater electrical power generation capacity to feed the advanced sensors, electronic warfare systems, and potential directed energy weapons that next-generation combat aircraft will carry. The digital engineering approach GE Aerospace has built around the XA102 program represents a meaningful departure from how complex turbofan engines have historically been developed. Model-based definition replaces the engineering drawing packages that have governed aerospace manufacturing for decades with three-dimensional digital models that carry all the geometric tolerance and manufacturing intent information that a drawing conveys, but in a format that integrates directly with computer-controlled manufacturing equipment, automated inspection systems, and simulation tools. Model-based manufacturing means production equipment receives instructions derived directly from the digital model rather than interpreted from drawings, reducing the transcription errors and interpretation variability that drawings introduce. Model-based inspection closes the loop by using the same digital model as the reference against which manufactured parts are measured and validated. The integrated result is a development and production system in which the digital model and the physical hardware stay in continuous correspondence throughout the program, enabling faster design iterations, earlier identification of manufacturing problems, and more confident validation of performance predictions before a physical engine runs on a test stand. The NGAP program that both GE Aerospace and Pratt & Whitney are competing in was structured from the outset around two parallel development tracks, maintaining competition through the technology maturation and risk reduction phase before an eventual downselect to a single engine design for production. In August 2022, the Department of War awarded $975 million contracts each to GE Aerospace and Pratt & Whitney to begin NGAP technology maturation and risk reduction, with Boeing, Lockheed Martin, and Northrop Grumman receiving parallel awards for associated systems work. Per the department's contracting announcement, Pratt & Whitney announced completion of its own Assembly Readiness Review for the competing XA103 engine in a separate announcement, meaning both competitors have now cleared the same milestone and both are positioning for the next program phase award anticipated later in 2026. The engine that wins NGAP will power whatever aircraft the Air Force fields as its next-generation fighter, a platform expected to succeed and complement the F-22 and F-35 in the 2030s and beyond. That production run measured against the scale of previous fighter engine programs represents decades of manufacturing sustainment and upgrade work worth tens of billions of dollars. Both GE Aerospace and Pratt & Whitney have invested heavily in digital engineering infrastructure, supply chain development, and test capabilities specifically to position themselves for this competition, and both companies' ARR completions indicate the programs are tracking on parallel schedules heading into the phase transition decision.